Dear students, so in previous class we were discussing about the closed set, the limit point and a closed set. Now we already proved that a closed sphere is also a closed set. Now in this class let us discuss about what about the intersection and the union of closed sets. In previous class we already proved that the union of open set is open and finite intersection of open set is open. Union of open set is open and the finite intersection of open set is open. Now here we consider what about the union of closed sets and intersection of closed sets. And there are, now let us go into an interesting result, that is any intersection of closed set is closed. In case of open set we will discuss that the finite intersection of open set is open. Only finite intersection of open set. But here we say that the any intersection of closed set is closed. How it is? Any intersection of closed set is closed means, let us consider f alpha, where alpha fall in some j means it's a collection, be the collection of closed sets in X. Collection of closed sets in X. Collection of closed sets in X. Now to prove that any intersection of closed sets means intersection f alpha where alpha fall in J which is closed. This is our requirement. Any intersection of closed set is closed. How to prove this one? So what about the intersection f alpha complement? To prove A is closed, it is enough to show that a complement is open. Why? Because we have a result. A is open if and only if a complement is closed, or A is closed if and only if a complement is open. So intersection over alpha f alpha complement equals union of alpha or union with respect to alpha f alpha complement. Why? Because we know that intersection of a complement equals union a complement for any set A. What about f alpha? Since f alpha is closed, we choose f alpha is a closed set. That's by your choice. F alpha closed means its complement. F alpha complement is open. And we also prove that union of open set is open. Any union of open set is open, therefore union of f alpha complement is open. Union of f alpha complement is open means the intersection f alpha complement is open. Intersection of alpha complement open means intersection with respect to alpha f alpha is closed. So any intersection of closed set is closed. Any union of open set is open. So similarly any intersection of closed set is closed. Okay. Also, we prove that finite intersection of open set is open. Here, what about the finite union of closed sets? Finite union of closed set is, by the same argument, we can prove that finite union of closed set is closed. So for letter f1, f2, etc., fn, with the finite collection of closed set in X. So now to show that intersection I ranges from 1 to n fi, which is closed. So this is our requirement. Finite union of closed set is closed. So each fi is closed. Fi is closed for I. Then to show that union I ranges from 1 to n fi is closed. So for what is actually union I ranges from 1 to n fi complement? That equals intersection I ranges from 1 to n fi complement. We know that since fi is closed, fi complement is open. Also we prove that finite intersection of open set is open. So clearly this right side is open, hence this one is open, means its complement is open, that means union I ranges from 1 to NFI is closed. Okay. So these are the 4 interesting results. That is, any union of open set is open, finite intersection of open set is open. Any intersection of closed set is closed, and finite union of closed set is closed. So these are the 4 interesting results. Okay. Now let us consider another result or another term, which is Cantor set. What is Cantor set? Cantor set means consider a closed interval 0 and 1, which is a closed interval. So you can divide this closed interval 0, 1 into 3 mutually disjoint intervals. That is closed 0, here it is 1 by 3, 2 by 3, 1. 0, 1 by 3, 2 by 3, 1. 1 by 3, 2 by 3, 1. You can divide the closed interval 0, 1 into 3 mutually disjoint open intervals. Open interval closed interval 0, 1 by 3, then open interval 1 by 3, 2 by 3, closed interval 2 by 3, 1. Then you can remove this middle third open interval 1 by 3, 2 by 3. So what remains here? Let F1 equals closed interval 0, 1. F1 is closed interval 0. Now divide this middle third open interval. Middle third open interval, here it is open interval 1 by 3, 2 by 3. What remains here? F2 is closed interval 0, 1 by 3, union closed interval 2 by 3, 1. Means from here you can remove the middle third open interval. Open interval 1 by 3, 2 by 3. You can remove it. What remains here? Remains closed interval 0, 1 by 3, union closed interval 2 by 3, 1. Okay. Now, what about again you can divide this removing the middle third open interval in closed interval 0, 1 by 3. Also remove the middle third open interval in closed interval 2 by 3, 1. Which is the middle third open interval 0, 1 by 3? The middle third open interval in 0, 1 by 3 is, it is 1 by 9, 2 by 9. That is the middle third open interval in 0, 1 by 3. And which is the middle third open interval in 2 by 3, 1? It is 7 by 9, open interval 7 by 9, 8 by 9. Enough. So from here, you can remove this open interval, middle third open interval 1 by 9, 2 by 9. What remains here? Then it is closed interval 0, 1 by 9, union closed interval 2 by 9, 1 by 3. 2 by 9, 1 by 3. Union, again, it is closed interval 2 by 3, 7 by 9, union closed interval 8 by 9, 1. Okay. So proceeding like this. Then this process can be continued indefinitely, and you can remove each middle third interval, or you can remove the middle third interval from each closed intervals. Then consider this here clearly. F1 is closed. F1 is closed. What is F2? F2 is a union of closed sets, that's again closed. F3, union of number of closed sets, which is also closed. Also we know that if we proceeding this, or if we continue this process indefinitely, then there are infinite number of such closed intervals. We also know that any union of closed set is closed. Therefore, each Fn is closed. Fn is closed for all n. Agreed. So let's consider f f equals intersection f. Intersection with respect to n, where n ranges from 1 to infinity, or intersection with respect to n. Means intersection, that is means this process continued indefinitely. Therefore, let f equals intersection fn. So this f is called a Cantor set. This f is called a Cantor set. So Cantor set means consider class interval 0, 1. You can first remove the middle third interval 1 by 3, 2 by 3, then proceeding or continues this process indefinitely. Finally, each fi is closed. Therefore, consider their intersection means infinite intersection of closed sets, that is known as the Cantor set. So f is intersection fn. This f is called the Cantor set. So Cantor set is closed. Each fn is closed. Okay, so this f is closed. F is closed. Clear? Okay. Now let S be the length of the intervals removed from closed interval 0. So what is the length of first middle third interval? The removed first middle third interval is open interval 1 by 3, 2 by 3. Whose length is 2 by 3 minus 1 by 3. It is 1 by 3. Plus. What is the length of 1 by 9, 2 by 9? This is the second middle third interval removed. So its length is 2 by 9 minus 1 by 9. It is 1 by 9 plus, that's a union, plus 8 by 9 minus 7 by 9, which is the next middle third interval that is removed. So its length is 8 by 9 minus 7 by 9, it is again 1 by 9. So 1 by 9 plus 1 by 9, so it is 2 into 1 by 9. Okay. Now the next the length of next middle third interval. The open middle third interval is, yes, it is 4 into 1 by 27 plus 6. Like this. Okay. So that means, S equals 1 by 3 into, it is 1 plus, can take 1 by 3 here. So it is 2 into 1 by 3 plus 4 into 1 by 3 whole square plus etc. Okay, so there is nothing but which is 1 by 3 into 1 plus 2 by 3 plus 2 by 3 whole square plus 2 by 3 whole cube plus etc. So what about the term inside this double bracket? There is nothing but a geometric series having common ratio 2 by 3 less than 1. What is the length of sum of infinite geometric series? Sum of infinite geometric series having common ratio r less than 1 is a by 1 minus r, where a be the first term. So here with this S equals a means 1 by S equals 1 by 3 into a means 1 by 1 minus 2 by 3. So equals 1 by 3 into 3 equals 1. So the sum of length of the middle third open intervals which is removed from this closed 0, 1, that's for the construction of Cantor set, whose length is 1. Also know that the Cantor set is uncountable and has its measure is 0. Okay, that are the 2 points. Now, let X be a metric space. Now consider another definition. X be a metric space. Let X be a metric space. A be a subspace of X. Then the set of all limit points of it. Set of all limit points of it. Set of all limit points of A is called a derived set of A. That's another important term. It is a derived set of A and is denoted by D of A. Derived set of A, it is called D of A. What is D of A? Derived set means set of all limit points of A. When X is a limit point of A, SR, the open sphere SRX contains at least one point of A other than X itself. So the set of all limit points of A is called the derived set of A, and which is denoted by D of A. Okay. Now by using this derived set, we define another term which is known as closure of a set. That is closure. CLOSUR, closure of A. If A is a part of X, X is a metric space, and clearly since X is a metric space, A is a part of X, then closure of A is denoted by this way. Just read it as A closure, known as read it as A closure, and A closure is defined as it is the union of A and its set of all limit points. The set of all limit points of A is a derived set of A, which is denoted by D of A, and closure of A is defined as it is the union of that set and its derived set. So A closure equals A union D of A. So A closure equals A union D of A means what is A? Clearly A is a part of A closure. It's an important research. A closure is A union D of A. A closure is A union D of A, and clearly A is a part of A closure. Okay. Is A closure is closed? A closure is a closed set. How to prove this one? To prove A closure is closed, it is enough to show that its complement is open. Okay. So for let X fall in. Let X fall in A closure complement. To show A closure is closed, first we show that A closure complement is open. Let X fall in A closure complement. X fall in A closure complement means X fall in A closure complement means X fall in what is A closure? It is A union D of A. A union D of A complement. X fall in A union D of A complement means what is A union D of A or complement? Which is X fall in A complement intersection D of A complement. By A union B complement is A complement intersection B complement. So that means X fall in A complement and X fall in D of A complement. X fall in A complement and X fall in D of A complement. X fall in A complement means clearly this X is outside of A. Okay. X fall in D of A complement means X is outside of D of A. X fall in D of A complement means X is outside of D of A. Agree? Now X is outside of D of A. X is outside. What is D of A? D of A means set of all limit points of A, derived set of A. So X is not fall in D of A means X is not a limit point of A. That implies X is not a limit point of A. X is not a limit point of A. Since X is not a limit point of A means there exists an open sphere having radius X such that SRX is a part of A complement. That means SRX intersection A is empty. SRX intersection A is empty. So SRX intersection A is empty means SRX is a part of A complement. Agree? Mark it as one. Now let Y fall in. Let Y fall in SRX. What is SRX? SRX is an open sphere centered at X having radius R which is positive. So that means there exists a R1 greater than 0 such that SR1Y is a part of SRX. Okay. But SRX is a part of A complement. That means SR1Y is a part of A complement. SR1Y is a part of A complement means SR1Y intersection A is empty. SR1Y intersection A is empty. SR1Y intersection A is empty means this Y is not a limit point of A. Y is not a limit point of A. Y is not a limit point of A. Y is not a limit point of A means Y is fall in D of A complement. Y is not a limit point of A means Y is the D of A complement. But what is Y? Y is chosen from where? Which is SRX. Y is in SRX. Same for Y fall in D of A complement. That means SRX is a part of D of A complement. SRX is a part of D of A complement means SRX is a part of D of A complement. Here SRX is a part of A complement. That means SRX is a part of A complement. That means SRX is a part of A complement intersection D of A complement. SRX is a part of A complement intersection D of A complement. A complement intersection D of A complement means it is A union D of A all complements. So SRX is a part of, that means SRX is a part of what is A union D of A? It is a closure complement. Means A closure complement has an open sphere with a center having center x and radius r which is greater than 0. That means A closure complement is open. A closure complement open means what is A closure? So A closure is closed. So this is the requirement. Hence the closure of a set. Closure is nothing but the closure of a set is the union of that set and its derived set. So A closure is A union D of A. Then clearly closure of a set is a closed set. Agree? Thank you.